Hello everyone, today we are going to looking into the next topic on elements of algebra, and the topic is mathematical induction. How exactly are we going to proceed this chapter? We will be looking into what exactly is mathematical induction, and then we'll try to see how mathematical induction is related to the principle of least element. What is the principle behind mathematical induction? We'll also try to see why mathematical induction holds correct, why this argument holds true. And then we'll try to see what is strong induction, what is weak induction. And then we'll do problems. We'll try to solve as many problems as possible. We'll be specifically looking into topics or the problems from the MIT course notes, and then we'll be looking into the questions from the number theory, famous number theory book by Burton. We'll try to solve all the questions, and then we'll end up this video, or maybe the next video we'll do is look into all the questions from mathematical induction in the last 40 years that were asked in IIT JEE. So that's how we are going to look into this topic. So, what is the principle behind mathematical induction, or what is mathematical induction first of all? So, mathematical induction principle in disguise is a least positive integer principle. So, what exactly I mean by that? Well, if you try to look into any of the set, let's say I'm taking a set of positive integers, some random positive integer, 1, 2, 9, 10, or maybe another 1, 3, 5, 8, 11. So whatever set I'm taking, always in this set of positive integer, definitely I have the smallest element. In this case I'm having the smallest element, this one. In this case the smallest element, this one. And if I have got the smallest element, I can generate the other element just by adding 1 to it. So from 1 to 2 I can get just by adding 1, from 2 to 9 I can get just by adding 1 plus 1 plus 1, and I can add it till 6 or 7 times to get to 9, and then addition 1 I will get 10. So what I mean to say is, if I got a set of positive integer and that set of positive integer have got the lowest element or the least element, and from the least element I can generate all other elements. So how this are related to mathematical induction, how this particular concept is related to mathematical induction, we'll try to see that. Apart from this, we also need to remember that mathematical principle in general, what exactly we do, we take discrete elements and then we try to prove the continuity of this statement using these discrete elements. So we are taking discrete elements and then trying to prove continuity of a statement, and that is the core behind mathematical induction. So what exactly I mean by this? So let's try to see how you need to solve problem using mathematical induction. So in order for you to solve problem using mathematical induction, the first and foremost thing we do is we try to see whether this statement holds true for the base case. What I mean to say is, let's say we all know that 1 plus 2 plus 3 all the way till n is equal to n plus 1 by 2. So if I am required to prove this statement using induction, so the first and foremost thing I need to do is I need to see whether this statement holds true for n equal to the base case. In this case the base case is 1, the first element, and for the first element the right hand side is only 1 and the left hand side is 1, 1 plus 1 by 2, which is, so 2 and 2 cancel, so 1 also I am having here, so left hand side is equal to right hand side. So the statement holds true for the base case. In this particular case, the base case is 1. So what exactly are we going to take the base case? That depends on the type of question we are solving. So we need to see whether the statement holds true for the base case. Once we are done with this, and if this turns out to be true, the next thing we need to do is we will try to see, or rather we'll assume that the statement holds true for n equal to n. In certain book you will find, and in certain book you will find that n is equal to k, where k is less than equal to n. So we'll try to prove the statement assuming that the statement holds true for n equal to n. So what I mean to say is, we'll try, in this particular case we'll say that, well, the summation of all the n from n equal to 1 to n is equal to n plus 1 by 2. So this we are assuming, and this is known as induction hypothesis. So this statement is known as induction hypothesis. So once we state this, next we'll try to use this argument to prove that the statement holds true for n equal to n plus 1. So then this turns out to be, and now I need to replace n with n plus 1, so this becomes n plus 1 and this becomes n plus 2 by 2. So now I need to prove this using this fact. I am assuming this is true, and using this fact that this statement holds true, I am using this fact to prove this. So how this turns out to be correct? Because I know that I can generate the next element just by adding number 1 to it. If I got the smallest element, I can generate the next element by adding 1 to it, and then the next element by adding to it, and this way I can proceed up to n elements. So here I am stating that the statement holds true for n equal to n, and if this statement holds true for n equal to n, using this fact, now I am replacing n with n plus 1, the next element. I am trying to see whether the statement holds true for n equal to n plus 1, and if the statement holds true for n equal to n plus 1, that implies that the statement would also hold true for the previous element. And if n plus 1 is correct, that means because I know that I can generate the next element just by adding 1 to it, that means even n plus 2 will be correct, and if n plus 2 is correct, similarly the next element n plus 3 will be correct, and henceforth everything will be correct. So that means if I can prove that the statement holds true for n equal to n plus 1, that means in general I can say, well, the principle or the statement would hold true for n equal to n. So that is the basic argument. Now why this argument would hold true? Why this logic shall hold true? And then first of all, how exactly we need to write this definition correctly using mathematical symbols. So the base case, in general, I am assuming the base case to be 0, so P0 is true. If P0 is true, and so this symbol stands for and. For all elements k, P of k, if this holds true, this implies P of k plus 1 must be true, and so this is what mathematically induction definition looks like. So I have got the base case, if the base case true, and for all value of k, if the pk, or in certain case I can also replace this k with n, and then I would say, well, if pn is true, then pn plus 1 must also hold true. So this is how we write the statement using mathematical notation. A very simple statement using mathematical induction, we write it this way. Now the first question comes is, why this argument or why this logic must hold true? What is the principle behind this logic? Why this must hold true? How can I conclude if P1 is true, Pn is true, then Pn plus 1 is also true? What is the logic? What is the argument? So The principle of mathematical induction is based on contradiction. So what we actually assume is, we assume that there happen to be some element, let's say the element is n0 in that set, which is false. We claim it, or we assume it. Let's say I'm writing it, we claim it. So this is the smallest element, and not is the smallest element of the set. And which set is this? This is the set of all elements when P of n is false. So this is the first element or the least element where the statement won't hold true, and all the elements prior to that should hold true. So if let's say n1 is an element which is less than n0, so Pn1 is true. But then if Pn1 is true, because I know I can generate the next element just by adding 1 to it, so Pn1 plus 1 is also true. And similarly, going this way, definitely I will reach a number which that number n0 will be only 1 less. The number will get a number, let's say the number is n dash, which definitely will be only 1 less than n0. So even in this case the statement will hold true, and if the statement holds true for n dash, so the statement must also hold true for n dash plus 1, and n dash plus 1 is n0, so that the statement must hold true for n0. But what we assumed or what we claimed is that the statement n0 Pn0 is false. So that means my claiming is wrong, or we arrived at a contradiction. So the statement must hold true for the next element, it must hold true for the next element, and this way for the entire n elements. So far, based on this logic, we'll try to do a problem, and the problem states that we are looking into summation of some number. Number is 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial, and we are adding it up all the way up to n into n factorial, and I claim that this should be equal to n plus 1 factorial minus 1. This is what I am required to prove using induction. So in order for me to prove this using induction, what the first thing I need to do is prove that case using the base element. So in this case the base element is 1. So let's say if I am using P1 base element, so in the left hand side I have got 1 into 1 factorial, which is 1, whereas in the right hand side I have got 1 plus 1 factorial minus 1, which is 2 factorial minus 1, which basically is 1. So left hand side and right hand side are equal, so the statement holds true for the base case. Now if the statement holds true for the base case, is the next step for me is I need to see whether, or rather I need to assume that this statement holds true for n equal to n. I am assuming. So this is my induction hypothesis. So I am assuming Pn is true. So by the way, this whole thing I can write the shortcut and say, well, this is equal to summation of n equal to 1 to n, and then we have got n into n factorial, which is equal to n plus 1 factorial minus 1. So this is the short form notation. So far we have proved that the statement holds true for the base case. We have proved P1 is true. Next, I am assuming that the statement holds true for n equal to n. So I am assuming now this statement is true. So this is called, or this statement is true. So this is known as induction hypothesis. Next, I need to prove that the statement also holds true for n equal to n plus 1. So if That means I need to replace this n equal to 1 to n plus 1, and here n plus 1 and then n plus 1 factorial. This should be equal to n. I need to replace this n with n plus 1, so this becomes n plus 1 plus 1, which is n plus 2 factorial minus 1. This is what I am required to prove. And I can prove this using this fact. So somehow I need to do some manipulation so that I can use this identity to somehow arrive at this conclusion. So let's start off with the left hand side. So left hand side, what I have got a summation of n plus 1 factorial, where n equal to 1 to n plus 1. So what basically this whole thing is, this actually is 1 into 1 factorial plus 1 into 2 factorial plus 2 into 2 factorial plus 3 into 3 factorial, all the way to n into n factorial, and then another n plus 1 into n plus 1 factorial. But from here to here I know, and then I claim that this holds true using the logic in the induction hypothesis, and I know that this is equal to n plus 1 factorial minus 1, so I can replace this whole thing with n plus 1 factorial minus 1 plus what extra thing I have got, a n plus 1 again, and then a n plus 1 factorial. Now, so I got a, so maybe I need to write it clearly here. So n plus 1 factorial minus n plus 1 factorial minus 1 plus a n plus 1 into n plus 1 factorial. And you can see here I got an n plus 1 factorial and n plus 1 factorial. Maybe I can take the n plus 1 factorial as common. So if I take this as common, so here I've got a 1, and then here I've got a n plus 1 and then a minus 1. So this is equal to n plus 1 factorial, and this basically is n plus 1 plus 1, which basically is n plus 2 minus 1. So which is actually n plus 1 factorial into n plus 2 minus 1. So n plus 2 into n plus 1 factorial basically is n plus 2 factorial minus 1, and this is what we are required to prove. So done. So this is how we need to prove. Maybe we can take another example. So all these examples, whatever I'm quoting, I got this from the MIT course notes. So I'm using all these examples from MIT course notes to show you the use of induction. Next, we'll try to prove this famous binomial identity plus n choose 1 plus n choose 2 all the way to n choose n is equal to 2 to the power n using induction. How can we prove this statement using induction? So again, base case. So what is the base case? In this particular case, I need to take n equal to 1. So base case, if n is equal to 1, so this becomes say 1 0, correct, plus a 1 1, which is 1 choose 0 and this. So this basically is 1 and this basically is 1, so this is 2. What about the left hand side? So this is the right hand side. What about the left hand side? So with n equal to 1, 2 to the power 1 is 2. So I have got left hand side which is equal to right hand side. So this statement holds true for n equal to 1. Now I am assuming that the statement holds true for n equal to n. So far what we have done, we have proved the base case. P1 is true. We have proved this. The next step is I am assuming that the statement holds true for n equal to n, induction hypothesis. So summation of n choose I equal to 0 to n, that should be equal to 2 to the power n. We are assuming this to be true using induction hypothesis. And I will be using this fact in order to prove the statement also holds true for n equal to n plus 1. So if the statement will, if I need to prove that, so what I am required to prove that the statement holds true I equal to 0 to n plus 1, and here n plus 1 I is equal to 2 to the power n plus 1. This is what we are required to prove. So maybe what I'm required to prove, I'm writing it here because the board is small. So maybe I will just write it here. So I'm required to prove that summation of I equal to 0 to n plus 1 and n plus 1 and I, which is equal to 2 to the power n plus 1. This is what we are required to prove. Okay, so how the thing would look like if I'm writing it, not in the compact form, if I'm expanding it. So this becomes say n plus 1 0 plus n plus 1 1 plus n plus 2 2 plus all the way, and then here I've got a n plus 1 again and a n plus 1 again. This is how it's going to look like. Then again, in order for me to prove this is equal to 2 to the power n plus 1, that's what I am required to prove. So in order to prove this from this, what exactly I need to do? I need to use the famous binomial identity that n choose 0 plus n choose 1 is equal to n plus 1 choose 1. So using this identity, so I'm writing the identity here. What identity I'm going to use, probably you can see it from here. I'm using that n choose k plus n choose k plus 1 is equal to n plus 1 k plus 1. I'm using this identity. So if I'm using this identity, so I can convert this n plus 1 0 with n 0, and this one 0 plus 1, and this one n1 plus n2, and all this way this one n plus 1 n plus n plus 1 n plus 1. Sorry, n with the n, this. Now this one definitely is equal to 0, so I don't need to worry about it. So what I end up getting is n0 plus 0 plus n1 plus n1 plus n2, and the next element again I will have another n2 and so on. So basically I have got a 2 set of this one. So because you can see here a two elements, and it will continue. So what I will have is a 2 set of this one. So this basically is n0 plus a n1 plus a n2 plus all the way to nn, and how many we are having? We are having total 2. How much this is using induction hypothesis? We know this value is equal to 2 to the power n into 2, which is 2 to the power n plus 1, and that's exactly what we are required to prove. So that's how we do problems in induction. So far what we have done are simple, easy examples. Gradually we'll look into more complex and difficult problems. Another identity we'll try to prove. 1 n choose 1 2 n2 plus a 3 n3 plus a 4 n4 all the way till n, and n is equal to n 2 to the power n minus 1. We are going to prove this identity using induction. We have got different ways and means to prove this. But induction, because we are dealing with induction, so we'll try to solve this using induction, which is a bit lengthy, but then we got no choice because right now we are in the topic mathematical induction. So again we are going to use the identity. Which identity are we going to use? N choose k plus n choose k plus 1 is equal to n plus 1 k plus 1. We are going to use this identity to prove this. Okay, same identity that we used in the last problem. So this is just a reminder what are we going to use. Okay, so we are trying to, so the first step is the best case. So we will look into the best case. If the best case is 1, so this becomes 1, 1, 1, which is 1. What about the right hand side? So this is what we get in the left hand side. What about the right hand side? Is 1, 2 to the power 1 minus 1 is 0. So this is 1 into 2 to the power 0, which is 1. So this statement holds true for n equal to n. Sorry, so the statement is correct for the base case. Now we assume that the statements hold true for n equal to n. So I am assuming this statement is true. So this is what we are claiming using induction hypothesis. So we need to prove that the statement is correct for n equal to n plus 1. So that means I need to replace this with a n plus 1, 1, this with the n plus 1, a 2, a 3 with n plus 1, 3, and this one a n plus 1 with the n plus 1 and another n plus 1, and that should be equal to a n plus 1 2 to the power n plus 1 minus 1, which is a n plus 1 into 2 to the power n. So this is what we are required to prove. So in order for me to prove this from this, how can I do? So as I mentioned, we are going to use the binomial relation. So this I can say, well, I can replace this n plus 1 with 1 as n0 and the n1. Plus here 1 plus 2, and this one I can replace with the n1 plus the n2, and the next digit I can replace with the n2 and the n3, and so on. I can replace the last element with the n plus 1 and the n with the n plus 1. And this I know is equal to 0, so I can ignore this. So we end up getting this many terms. So what I get is 1 n into 0, then n1 I have got 1 here, and then I have got another 2 here, so total 3. So plus 3. Here I have got 2, and here I have got another 3, so plus 5 and 2, and similarly we'll get this. So we'll get 2n plus 1 using the fact that it's 1, 3, 5, which basically is a odd number series, so it's of the form 2n plus 1, and here I will have a n with a n. Now you can see here I've got a 3, I've got a 5, 1, so maybe I can take each one separately, and then I can say, well, this is equal to a n0 plus a n1 plus a n2 and a nn. And how much extra we are having? Extra we are having another 2 and 1 and a 4 and 2 plus all the way to n and n. And now maybe I will rub this portion. So remember, this is what I am required to prove. So I am removing the remaining portion. So this is what we were required to prove. So from here to here we have just proved in the last example that this is equal to what is the value 2 to the power n. And from here to here I can take the 2 common, and then I can write this is equal to 2n plus n2 n3 and n. So this is what I can make out of this with taking 2 as common. So taking 2 as common, so I've got a 2, I've got another, so a 2, a 4 and a n. So this is what we end up getting. So this exactly is this series, and this series is equal to n 2 to the power n minus 1, and then here I have got a 2 here, and then extra what thing I am having plus a 2 to the power n, this portion. So total what I am having now is 2 to the power n plus 2 into n into 2 to the power n minus 1. And this is what I am having. Oh well, so 2 to the power n plus 2 into n into 2 to the power n minus 1 is what we are having. So from here I can take the 2 common, 2 to the power n common, and this I can write well 1 plus, here I can, if I am taking 2 to the power n minus n as common, so here it should be a half, because for this the 2 already as it is and a n. So this is 2 to the power n, and this 2 cancel, so I am left with 1 plus n. So 1 plus n, so this is what I have got now, and this is exactly what I am required to prove. So we are done. So this is how we need to do problems involving induction. Sometimes while doing problems I forget what exactly I was telling, so that's why the little bit of pause in between the sentence, because I forgot what I was telling. So next we'll look into the concept of strong induction and weak induction. So we'll look into the topic strong induction. So induction topic basically divided into 2 parts. One is strong induction and another is weak induction. Strong induction and weak induction. So what exactly is strong induction and what exactly is weak induction? Let's say you are required to solve a statement. How do we solve the statement? We assume that the statement holds true for the base case, and then we assume that the statement is true for n, and then so that was the induction hypothesis step, and then we try to prove that the statement holds true for n equal to n plus 1. Now in doing so, what exactly, or how can we probably have some intuitive idea behind induction is what exactly we do. Let's say we can think of these as stairs. So let us assume this is the base case, and in order for you to climb this ladder, the first thing you need to do is step on the first step. So this first step is equivalent to your base case, and then the induction hypothesis is similar to the concept that what we normally assume that this using induction hypothesis, that the statement holds true. So that is equivalent to say that these stairs exist. Now the difference between strong induction and weak induction is, in case of strong induction, we need to consider each of these steps. So all the steps that you were about to climb, we will be proving that these steps exist. Whereas in case of a weak induction, we assume all these steps to exist, and then we assume that we only assume the statement that we are, or the steps that we are currently stepping on. And the inductive step is going up further, we try to prove one more step exists. So what exactly I mean? Strong induction and weak induction, the basic difference lies in case of weak induction, we ignore all these steps, the in-between step. The best step exists, where I am standing now exists, and I need to prove the next step exists. Whereas in case of a strong induction, I need to prove this is existing, the best case, this one exists, this one exists, this one exists, this one exists. So all the in-between step also exist, and the steps on which now I am standing or stepping on is true, because all these were true, and now I need to prove that the next step also exists. So that is the basic difference between strong induction and weak induction. To give you an example of strong induction, what do you call that, an example of using strong induction to solve problems. So assume that I am required to prove that any number greater than 2 can be factored into prime. So we are proving that all numbers greater than 2 can be factored into prime. So all numbers, this is what I am required to prove, all numbers greater than equal to 2 can be factored into primes. What I mean by this is, let's say if I got a 2, so I know it's 2 equal to 2 into 1, so I got a prime here. If I let's say take 8, so 2 into 2 into 2, so prime again. If I take 10, 2 into 5, prime. So all numbers greater than 2 can be factored in terms of prime. That's what we are going to prove using induction. Base case. The base case is n equal to 2, and we know 2 is equal to 2 into 1 can be factored in terms of prime, so the base case holds true. Now I am assuming that this statement, now I cannot assume, I need to prove, or I am assuming now this statement holds true for all the integers up to n. All the integers up to n, this statement holds true. And I need to prove that this statement will also hold true for n equal to n plus 1. So I am assuming the statement holds true. Not I am assuming, I am taking it for granted that this statement holds true for all integers greater than equal to, less than equal to n, for all integers less than equal to n. So all these integers which are less than equal to n, this statement holds true. So that's what I am claiming. So this is my induction hypothesis state, and using this claim I need to prove that this statement will also hold true for n equal to n plus 1. So this is my induction hypothesis, and I need to prove that this statement will also hold true for n equal to n plus 1. Now, case 1, there are two possible cases. That n plus 1 will have prime factors. if that is the case, if n plus 1 is having prime factor, so that means I am not required to prove anything, I am done. Another case is n plus 1 do not have prime factors. So if n plus 1 do not have prime factors, that means I can break down this n plus 1 into two different prime factors, p1 and p2, and definitely this p1 and p2 are less than n plus 1, and since my statement, because I use strong induction, and using strong induction I assume that the statement holds true for all the elements less than equal to n, and quite natural, p1 and p2 definitely are always less than equal to this n value that we assume to be the case. So that means this and this. So because n plus 1, if they do not have prime, so I can break it down into p1 and p2, and p1 and p2 can themselves be factored into prime because that holds true. So that means p n plus 1 is true. So that means p n plus 1 is true. So what I did, I am assuming that the statement holds true for n equal to 2 base case, then I assume that the statement would hold true for all the elements up to n, and then I am trying to prove that the statement would hold true for n equal to n plus 1. So if that n plus 1 is an element, there are two possible cases. The n plus 1, it could be prime, or it might not be prime. So if it is a prime, so that means we can definitely, it has got the prime factors. And if it is not a prime, so I can always break it down into two prime factors, p1 and p2. And p1 and p2 themselves, because these numbers are less than n, and I assume that these numbers were or could be factored into prime. So that means because n plus 1 is made up of p1 and p2, and p1 and p2 are or were factored in, or can be factored into prime, so that means n plus 1 can be factored into prime
as well. So that means the statement holds true for n equal to n plus 1.